Great. Thanks, Anthony. We are really excited for Dai to give this presentation today, especially on April 1st. Before jumping in, this is kind of our nominal intro slide that we have. We hold these seminars throughout the year, so if this is the first time joining us, please check out our website and you can see the upcoming schedule. I've copied it down to the bottom left. You can see that Matt Lang is giving a seminar next month on May 6th. We advertise these talks to our mailing list, so if you haven't signed up, please do so. And then if you know anyone that is interested in kind of data assimilation throughout geospace science, feel free to reach out to us with their names or your names, and we'll try to get you on the schedule then. And like always, we record these talks and then upload them to our YouTube channel. So if you're coming here now and then see a talk that you've wanted to watch in the past, feel free to go over there and check it out. Really excited to introduce our speaker today, Dai Koshin at NCAR. He's done a lot of work on kind of neutral atmosphere and thermospheric dynamics, and is going to tell us about their recent paper that's just published or about to be published on the JAGUAR-DAS whole atmosphere reanalysis. And please feel free to ask questions during the talk. You can either put them in the chat or raise your hand, and we will be monitoring that and take that away. So I'll stop screen sharing here, and Dai, that the seminar is all yours.
So, can you see my screen?
Yeah, it looks great.
Okay, so let's talk. So thank you for the opportunity and thank you for the coming to today's talk. So I will talk about the JAGUAR-DAS whole neutral atmosphere analysis called JAWARA. So this is a collaborative work with me and some people from University of Tokyo and Jamstec and JPL. So this is a description paper of our data. So if you are interested in, please read this paper. And the data, our data is also published online. So if you access to, if you go to this website, you can download the whole data of our. So please, if you are interested in, please go to this site or go to read this paper. So first of all, I will talk about the vertical layer of the atmosphere, because not so many people are familiar with the middle atmosphere. So I think some of the people, the audiences are more familiar with more upper atmosphere. So I will talk a little brief introduction. So that for the definition by the altitude, the upper atmosphere has the altitude above 100 kilometers. In this altitude, there are some thermosphere and some another region of the atmosphere. And the middle region is called the middle atmosphere. It is correspond to the stratosphere and mesosphere and lower thermosphere region. And lower atmosphere correspond to the troposphere. And there are several another classification. One is a homosphere. So in the homosphere around this altitude, the concentration of the atmospheric position is almost uniform. And the other classification is the neutral atmosphere. Neutral atmosphere is in this altitude region. In this altitude, the contribution of the ionization is relatively low, so it is called neutral. Now, for today's talk, I'm mainly focusing on the middle atmosphere dynamics. So in this altitude, there are several meridional circulation and several kinds of waves. This is the latitude and altitude section of the global structure of the middle atmosphere, mainly for the middle atmosphere. So there are some large-scale circulation in the upper mesosphere and also in the stratosphere. And these large circulations are mainly driven by some kind of waves, like gravity waves and some tidal waves or some Rossby scale waves. The right panel is also shows the latitude and height section of some fluctuation or some variation in the middle atmosphere or some another region. So that one of the examples is quasi-biennial oscillation, and sudden stochastic warming is also a large-scale dynamic. And also there are some interaction with NCAR with some upper altitude. So these meridional circulation and so large-scale oscillation are mainly forced by waves propagating mainly from the lower atmosphere. And the role of these waves, their modulation is important for the middle atmosphere, especially for the vertical coupling or some inter-hemispheric coupling. So in this figure, these are the example of the observation to observe the middle atmosphere. These are the ground-based observation, and these are the satellite observation. So the observation has very wide range, but not all observation can cover all of the height of the altitude. So some of the altitude is difficult to observe. So there may be some difficulty for the middle atmosphere study. For the observational study, I have already shown in the previous slide, the number of the instrument is quite limited. If you consider the radar or LiDAR, it can observe the continuously, and it has very high resolution and high accuracy, but the distribution is sparse. For satellite observation, you can make global distribution, but the density of the observation is sparse in space and also in time. On the other hand, several studies using some general circulation model GCM for the study of the middle atmosphere. You can obtain global grid data by using GCM, but there are some limitations. If you use the low resolution GCM, they are not so mature, especially for the gravity wave parameterization and several other parameterizations. And it has very large model discrepancies. If you use the high resolution GCM that explicitly treats gravity waves, this problem is not important, but this problem was partly solved. But due to the high computational cost, only for few simulations of specific data is possible. So it is difficult to make longer time period simulation. So considering these two problems for observation and GCM, it is not surprising that data simulation has the potential to solve these problems. For the study of the lower or more weather or meteorological study, the analysis dataset have been used for a wide range for atmospheric and also for climate research. So here shows some coverage of the atmospheric reanalysis, conventional reanalysis. The most famous one is ERA 5 that covers for very long time period from 1940 to the present, that covers up to the altitude about 40 kilometers. It is around Stratford region. And there are another atmospheric reanalysis like JAWARA-3Q and MERA-2 data. This data covers the altitude around 80 kilometers up to the upper atmosphere region, and it also covers very long time period for 1947 for JAWARA-3Q or 1980 to MERA-2. So my focus is a little more high altitude, so the target for JAWARA is here. Although the beginning of the time period is 2004, it is related to the assimilated observational data, and the coverage of the altitude is 110 kilometers. So a little more higher altitude coverage is the advantage. And there are several recent studies that focus on the middle atmosphere analysis. One is NavGem HA, and the other is Wacom XStat, and JAWARA is here. So there are three three studies that focusing on the altitude around the above the mesosphere, above the mesopause region. So I will show the more detail about the configuration of the JAGUAR data assimilation system called JAGUAR-DAS. The forecast model of this data assimilation system is a Japanese atmospheric TCM for upper atmosphere research called JAGUAR. The model top of this TCM is about 150 kilometers, and horizontal resolution is about 300 kilometers, and vertical resolution is about 1 kilometer. It also uses several radiation processes for MLT region. It is important in the MLT region, so non-LTE and several ozone and O2 heating. And it also has some gravity wave parameterization for holographic gravity wave and non-holographic gravity wave. The data assimilation module is a four-dimensional local ensemble transform Kalman filter called 4D LEDKF. The number of ensembles is 50, and the analysis is updated by using incremental analysis update. The advantage of this 4D LEDKF data assimilation module is a low computational cost, so it enables the long-term it enables to make long-term reanalysis dataset. So the time period is started from September 2004 to the present. So we can produce the data assimilation reanalysis for about 20 years. This module is widely used to some global or regional models. So there may be some large application of this data assimilation system. And I will talk about the observation assimilated for the JAGUAR data assimilation system. One of the observation is ground-based, more conventional observational dataset, and the other three observational data are satellite observation. The PREP-buffer is a conventional dataset that covers the height range from the ground to the stratosphere region. It has several variables like temperature and zonal wind and meridional wind and relative humidity and surface pressure. It is a combination of several methods of observation like radio sonde, aircraft, and wind profiler, and so on. The second one is the Aura MLS that covers altitude from 20 kilometers up to 100 kilometers. We use the temperature retriever, and it is retrieved by the remote observation of ozone, O2 or O2. The third one is time saver that covers altitude from about 15 kilometers up to 110 kilometers. We also use the temperature retriever. Yeah, and the last one is DMSP SSMIS. It covers altitude from 30 kilometers up to 80 kilometers. In this observation, we assimilated the brightness temperature. It is also called as the radiance. In this SSMIS observed a little more nadir observation. So it has more denser, more large number of the observation for the long cross-track direction. So there are several differences for these three types of the satellite observation. And I will show the results. So for the beginning of this talk, I will show the basic characteristics of our data. This is a result of the temperature for the northern polar region. The time and height section of the zonal mean temperature is shown here. The time period in this figure that covers the entire time period from 2004 to the end of 2023. The first column is the result from JAWARA, and the next two columns with time saver and Aura MLS. So these are the observations that are assimilated to JAWARA data. The lower three as a conventional reanalysis dataset, MERA2, ERA5, and ERA55. And the right panel is the same figure for the zonal mean for the northern high latitude region. So from these figures, we can see very clear seasonal variation. So the temperature has very clear 1 year cycle. So it is warm stratopause is observed in summer, and the cold stratopause is also observed in winter. So the stratopause is going down and up and down and up in winter and summer seasons. It is also observed for the severe another observation and analysis set. For the zonal wind, in the most of the middle atmosphere, the zonal wind is westward in summer and eastward in winter. So there are also some 1 year cycle from eastward, westward, eastward, westward for the altitude from 20 to 90 kilometers. And we can also observe some wind reversal in the lower atmosphere region. In summer, the altitude is about 90 kilometers, and in winter, the altitude is a little higher for around 100 kilometers. So this variation is also observed for several other observations and reanalysis. And in addition to the seasonal variation, we can also observe some short-term variation. The most dominant one is the SSW. So we can see some descending of the stratopause like here, and also observed here, and here, and here, and also this year, and this year, and this year. So the descending of the stratopause in winter corresponds to the southern stratigraphic warming. So these characteristics are consistent with another observation or conventional analysis set. It is also reproduced in the JAWARA data. And at that time, the eastward wind becomes weaker around here, and also here, and here, and here. So it is consistent with the characteristic of SSW that weakens the zonal wind. The next one is the same, but for the equatorial region. So here shows the temperature for the equatorial region, the time and height section of temperature, and the time and height section of zonal wind. For the zonal wind, as the zonal wind was for the satellite observation is derived by the gradient wind. So in the equatorial region, the gradient is not calculated. So only for the comparison with, mainly for the comparison with conventional reanalysis is shown here. So in the equatorial region, the 1 year cycle of temperature or zonal wind is not so clear, but we can observe several interseasonal variations. For example, in the stratosphere, we can see that the eastward and westward wind are alternately descend. That is well-known structure called quasi-biennial association, QBO. We can observe the structure of QBO in our data and also in conventional analysis set. And the QBO is not so always smooth, so there may be some disruption and here, and also some disruption around these years. In addition to the stratosphere, we can also observe another structure in upper stratosphere region. In this region, the periodic eastward wind is observed. That corresponds to the stratospheric semi-annual oscillation, SSAO. The structure is, the SSO is, so is observed around this altitude region, or this altitude region. The SSO is also observed for the temperature, but although it is not so clear, but we can see some semi-annual fluctuation in temperature in the equatorial stratosphere. And in upper mesosphere, we can see another periodic westward wind fluctuation that corresponds to the MSO in the mesosphere, or mesopause SO is shown here. Although the mesopause region is not covered in these conventional analysis sets, but JAWARA data can produce the MSO structure in this altitude. And in the lower thermosphere region, I think we can see some cold, warm, cold, warm structure in the temperature in the lower thermosphere region. So we can assume that this is related to some solar cycle because the JAWARA, the forecast model of JAWARA does not consider the solar cycle, but the observation for the time of the saber or aura MS includes some information of the solar cycle, so it can be reproduced in the reanalysis data set. The last one is the southern hemisphere. So the temperature and zonal wind for the southern high latitude region. The seasonal variation is almost similar to the in northern hemisphere. So we can see the stratpose is downward, upward, downward, upward. So we can see 1 year cycle, and also the zonal wind in the middle atmosphere is westward, eastward, westward, eastward. So there are some 1 year cycle. The difference to the northern hemisphere is that the southern stratospheric warming is not seen in this figure, although there are some very small warming, but it is not so large comparing with the northern hemisphere. And eastward wind is more stronger in winter comparing with that in the northern hemisphere. And the altitude of the the altitude of the winter wind, that means here, so the altitude of the winter wind reversal, that means the reversal from the eastward to the westward is a little higher, or a little higher altitude. We also compare the longitude and height section of our data with the same data set. So this figure shows the meridional structure. The color shows the temperature, and the color contour shows the zonal mean, zonal wind. The upper panel is the result for DJF December, January, February for JAWARA, SEBA, MLS, MERA2, ERA5, and JERA55. The second one is March, April, May, and the third one is June, July, August, and the last one is September, October, November. So yeah, first of all, the overall structure is similar. And for detail, for DJF, we can see very strong eastward wind in the northern hemisphere, and we can see some large westward wind in the southern hemisphere. It is also consistent for these data sets. Although there are some differences, right? Because westward wind in the southern polar stratosphere is relatively weak in JAWARA data, but almost similar. For MAM season, there are some slight difference in the shape of the westward wind in the equatorial stratosphere. It should be related to the structure of the QBO, but almost similar for these. Although there are some small difference, but the overall structure is similar. For JJ, we can see very strong polar night state observed in the southern hemisphere, and the structure is similar for these data sets. And also, we can observe the westward wind in the northern hemisphere. That is also similar. Yeah, for the SON, we can see very similar structure for these data sets. Some people may be interested in the large warm temperature anomaly observed in SEBA in the summer polar region of the here or here and here. In this region, this data is not well assimilated for the JAWARA data because it has very large uncertainty. It has very large error, so it is not well assimilated in the JAWARA data. But this process is highly important because it is related to the geomagnetic fitting. But it is not considered in the forecast model of the JAWARA dataset, so there may be some discrepancy of these two. Let's say. We also compare some dynamic variables. So this is the example. One of the examples is the EP flux, and the arrow is showing the EP flux, and the color is showing the EP flux divergence for JAWARA, MERA2, ERA5, and JERA55. The satellite observation is not shown here. For the left upper panel is a comparison for JGA season. The second one is the MAM season, and this one is JHA season, and the right lower panel is the result for SON season. Sorry, I think this is the result for DJF season, not for JJ season. So we can see that typical structure for each season is observed. So we can see negative. That means the westward forcing in the winter stratosphere. That is also observed for the winter. So winter is here and also winter is here. So we can see some large negative forcing in the winter stratosphere. And although there may be some differences between some analysis, the analysis. So yeah, it is not the main focus of this paper, but several previous studies has already indicated there may be some difference by the intercomparison of these the analysis. This is the result for the residual mean circulation for DJF, MM, JJ, and SON. So we can see, although, I can say that the typical structure for each season is similar. So we can see the period of circulation in the stratosphere. So we can see some in the stratosphere, we can see large circulation in the winter hemisphere and small circulation in summer hemisphere. It is also observed in the large circulation in summer hemisphere and small circulation in the winter hemisphere, in the summer hemisphere. And the circulation, the large size of the circulation is almost similar in the MM and SON season. And in the mesosphere region, we can see large summer to winter circulation in this altitude. It is also observed the lower part of this circulation is obtained by MERA2 or some analysis, but a little in the more higher altitude, we can see large circulation from the summer hemisphere to the winter hemisphere. It is also observed. Summer to winter hemisphere is also shown. So in this figure, the color is the W bar star, so particle component of the meridional residual mean circulation, and the contour is showing the stream function of the residual mean circulation. So we can obtain that result that overall structure is similar, and there may be some difference among some of the analysis. So in this figure, we can obtain the wide height region, the distribution of the wide height region of the meridional or residual mean circulation by using JAWARA. So I checked the residual mean vertical flow in the northern high latitude. This is the result for the time and height section of the W bar star in the northern polar region from JAWARA data. W bar star is important because it is highly related to the adiabatic heating or cooling, and it is also related to the transportation of atmospheric constituents. So it is important for considering the vertical coupling between the middle atmosphere with the upper atmosphere. So this figure shows the vertical structure of W bar star. So we can see very clear seasonal variation. The upwelling is observed in summer and downwelling is observed in winter. So upwelling, downwelling. So there may be quite large seasonal variation. Seasonal variation is dominant. So I take the anomaly from the climatology. So it is shown. This lower panel shows the anomaly of W bar star. That the seasonal variation is subtracted. So the anomaly from the seasonal cycle is shown here. So we can see some short-term variation. One of the largest one is the negative anomalies that descend from 100 kilometers to 50 kilometers. So this is the example. And then in some another region. So like here, but also we can also observe some descent of negative W bar star anomaly from the lower thermosphere to the stratosphere, upper stratosphere, also for here and also here. So this is the W bar star anomaly, and I will also show the temperature. Here shows the zonal mean the distribution of the zonal mean temperature that I have already shown in several in previous slides. So this event looks related to the descent of related to the SSW for example, here, and also here, and here, and here, and also these years, we can see the descent of stratopause, and we can also observe the elevated stratopause in the altitude around 90 kilometers, and that also descends downward. So the formation and descent of the elevated stratopause, this altitude region looks related to this large negative double bar star in this region, although the mechanism is not well known, but the pattern of distribution looks related between these two figures. So that may be related to each other. And we also made some intercomparison with this middle atmosphere analysis. This figure shows the result of the intercomparison. The left four panels is showing the latitude and height section of temperature from NAVGEM-HA and MERA2 and the JAGUAR-DAS JAWARA data and WACOM-XR. This is the result for only for the DTF from 2009 to 2010. And the right panel is also showing the result for zonal mean for NAVGEM-HA, MERA2, and JAGUAR-DAS and WACOM-XR. As a conclusion, the structure is generally good in a good agreement, although some discrepancies are observed in the MLT region. But yeah, which are owing to the difference of the assimilated satellite data, and also there may be some difference of the forecast model, but they are in a good agreement. And in this paper, the wave activity is also compared and confirmed that they are in a good correspondence. So I have shown the result or overview of our data, and I would like to introduce some usage of our data. One of the usage is the analysis of middle atmosphere phenomena. There may be some different, here shows some example. So intra-seasonal oscillation in the MLT region and in the hemisphere coupling during the Australian winter. That is my work, and there may be some another work related to the normal model of waves and SW2 modulation, analysis of the SW2 modulation during SSW, and also there may be some analysis for the extreme westward wind event. This work is published today, and there may be some analysis for MQBO, and this JAWARA data is also used for the initialization for high-resolution numerical model simulation that focusing on the SSW and the IHC, or some studies focusing on the holographic gravity wave. So these studies are already ongoing work, but I am interested in some future work related to the analysis of atmosphere phenomena observed from ground-based observation, or some studies of thermosphere ionosphere coupling, or space weather and improvement in height of TCM, and also interested in some assessment of the impact of the observing system, evaluation of the uncertainty from the analysis and forecast error. So it is important for the update for the data assimilation system. So I will briefly show some showcase of the ongoing work or already published work that has already that uses the JAWARA data. So this is the example for MLT ISO. In the MLT region, it is known that there may be some intra-seasonal oscillation. This is a result of MLS temperature in the equatorial region for the time and height section. It is not so clear from this figure, but if you take the anomaly for the only for using the small scale or small short time variability, you can obtain some intra-seasonal variation in this altitude region. These in the color is showing the short-term variation, and the contour is showing the long-term variation. So we can see some short-term variation in the around region, and that propagates downward. We also confirm the latitude and height section of the distribution that are associated with this ISO. So this is the result for the temperature in June, July, August season that is associated with ISO. The phase of the ISO is classified into 8 phases, like the phase of the QBO or some MJO or some another cyclic oscillation. So we can obtain some meridional structure that associated with the ISO. So we can see some pattern, not only in the equatorial region, but that extends into the northern hemisphere and also southern hemisphere, and also in the winter stratosphere region. And that also descends with the progression of the phase. And we can also observe the zonal wind is also related to, associated with the variation of the ISO in the equatorial MLT region. We can observe some structure that extends into the winter stratosphere. And in this paper, we analyze some momentum budget. So as a result, this ISO looks mainly driven by the gravity wave forcing that is expressed by the parameterization, or the data estimation increment is also important. Another example is interhemispheric coupling. In this paper, in this study, we focused on the austral winter case. Using JAWARA data for 15 years, 7 austral winter warming, drastic warming is analyzed. These are the composite for IHC events. So we can observe some, this is a composite for temperature. The onset of the IHC event is set as day. So before and after the IHC event is shown here. This is the result for the composite for zonal wind. These are the typical structure in this season. And this one, these figures show the anomaly for the IHC event. So we can see warming around this region in the winter stratosphere. And also we can observe some cooling in here, and the warming is here. So this warming is related to the interhemispheric coupling. So we can see that the warming from here, and there is another warming that is a response of the interhemispheric coupling. In this study, we analyzed this IHC event in austral winter, and overall IHC scenario is similar to that in the polar winter. That the warming here that starts at the low altitude comparing that in the northern hemisphere. That is one of the differences. And the response in the summer upper hemisphere depends on seasonal variation of the wave activity. So in the scenario of the IHC, the quasi to the wave and also gravity forcing is known to be important, but there may be some seasonal variation. So there may be some difference in the austral winter. The scenario is more affected by the seasonal variation in the summer hemisphere. And the other example is the normal model of the wave. In this study, we have focused on the zonal wave number 1, must be gravity waves. This normal mode has a period of 1.3 days, and that has a structure like here. Here shows the contour shows the potential height associated with this must be gravity wave mode at the altitude of 80 kilometers. And the color is showing the zonal wind and meridional wind. And this is the time progression. So this pattern moves to westward with the time progression. And they also show that this structure is almost barotropic. In addition, there are some seasonal variation. So these are the amplitude distribution for the 1 year climatology from January to December, and South Pole to the North Pole for several altitudes. In the stratosphere, the amplitude is large in winter, like here, and also like here. But in mesosphere, the amplitude is larger in winter and also larger in summer, so there may be some difference. Currently, we are studying about other normal mode component not only for the low speed gravity wave one, but we are studying about several another normal mode component. And the last one is the SW2 modulation during SSW. It is known that after the SSW static warming, there are some amplification of SW2 component, semi-diurnal wave number 2 tidal wave is amplified. This study focused on several events during 2006, 2009, 2013, and 2019. So this is the time and height section of the zonal mean zonal temperature from JAWARA data. And there are some static warming and elevated transport is also observed here. So the advantage of JAWARA data is the hourly data, so we can obtain more detailed or more higher frequency analysis is possible using JAWARA data. So as a result, this figure shows the amplitude, time, and latitude distribution of the amplitude of SW2 after the onset of SSW. The amplitude of SW2 is increased. And this is the phase of SW2 component. So after the onset of SSW, the phase of SW2 became more antisymmetric. These are the amplitude before and after the onset of SSW, and these are the phase latitude and height distribution of the phase before and after the onset of SSW. In addition, for these characteristics, the cooling during elevated transport here looks related to this enhancement. So this is a latitude and height section of the correlation between the amplitude of SSW2 and the temperature in our data. So there may be some large negative correlation is observed. So the cooling around this region looks related to the amplification of the SW2. So yeah, currently we are focusing on more further study for this modulation of SW2 or another component of tidal waves. So this is the summary of my talk. So the first, our data have been produced for about 20 years from September 2004 to the present. So this is the first long-term analysis for the whole region of the neutral atmosphere. And we made some validation against satellite observation and conventional analysis datasets. The seasonal variation of temperature and zonal wind are consistent with these compared datasets. And also the meridional structure of temperature, zonal wind, circulation, and the flux divergence are also in a good agreement. We compare the seasonal variation of W bar star in the northern polar region, and it shows some strong downwelling in winter that is associated with SSW. And several studies using our data have started. These studies are mainly focusing on the phenomena in the middle atmosphere. So future studies for ionosphere, thermosphere analysis are also welcome. And this is a very important point of this talk, today's talk, because our data is openly available. So you can, if you are interested in, I will appreciate it if you go to this website and download our data for your study. So that's all for my talk today. So thank you for listening.
All right, thank you very much, Dai. Do we have any questions from the audience?
Like a comment, just really wonderful talk, honestly. It's a lot of work. These reanalyses are incredibly complicated and challenging to put together. I'm just a bit silent maybe because I'm now trawling through the website you put at the end there. So you've got the whole data record from 2004 to 2024 in there. That's correct?
Yeah, we produced the data from September 2004, and after the data after 2024 or 2025 is also in progress. So we are updating the end of the data, and we can published this data all of the time period. You can download all of the data.
Really great work. Thanks. I'll probably be reaching out at some point.
Is that can I is there a question? Yeah, I couldn't. That's
I don't think so. I think everyone's still processing. Cool.
We
Last
have a
call.
lot of people that tend to watch these the recording afterward.
that's
Often we
very
can ask questions afterward. So yeah, I know at least a dozen people who end up just watching the recording rather than coming live. So
Yeah. I don't recall, but did you include your email on one of the first slides, just in case anyone wants to reach out afterwards after watching later?
Oh, does it mean my email address?
Yeah.
Yeah, I think it's a very good idea. So
Sure. If it's on one of the first slides, then we can refer people back to the beginning, or if we can jump to it really quick to have it on screen.
do you mean this one?
Yeah. Okay, no email, but if you want to provide it, feel free, although it will go on YouTube, so it's up to you. If it should be easy to find you through the HAO website, then maybe that's a good option too.
I see.
All right. Well, if there's no other questions, let's thank Dai again for a really wonderful talk, and thank you so much for the talk and making everything so publicly available for us to access. So thank you. Thanks everyone for joining virtually, and hopefully we'll see everyone next May 6th, the next talk by Matt Lang. So thanks again, Dai, and see you all in 1 month.
Thank you very much.
Kai.